Tonight, we're going to look at something strange happening in the sky above Mars. NASA's Curiosity rover has photographed thin, iridescent clouds glowing with pinks, greens, and blues high above Gale Crater. They form roughly 60 to 80 kilometers above the Martian surface. And unlike most clouds we are familiar with on Earth, many of these appear to be made from crystals of frozen carbon dioxide, essentially dry ice. The colors are real. They appear when sunlight passes through cloud particles that are unusually similar in size, producing the shimmering effect scientists call iridescence. But the colors are only the beginning of the mystery. According to our current understanding of the Martian atmosphere, carbon dioxide should not be freezing into clouds so easily at these altitudes above Gale Crater. Something appears to be cooling pockets of the atmosphere more than scientists expected. Curiosity has now seen these clouds return during the same Martian season, while NASA's Perseverance rover, operating elsewhere on Mars, has not seen the same phenomenon. Researchers have ideas about what might be happening, including powerful atmospheric waves moving through the Martian sky. But they still cannot fully explain why these clouds form where they do, why they appear so regularly, or why one part of Mars seems to produce them while another does not. And that makes these beautiful clouds much more than an unusual photograph. They are giving us a glimpse into a Martian atmosphere that is still more complicated, more active, and less understood than it first appears. By the end of tonight, we're going to understand what these strange clouds are made of, why their colors matter, what may be creating them, and what they can tell us about the climate and atmosphere of Mars today. Before we continue, if you enjoy exploring the quieter mysteries of space with us, take a moment to like the video or subscribe. It helps the channel reach more people who enjoy learning about the universe at a slower pace. The observation that brought renewed attention to these clouds happened on January 17, 2025. It was Sol 4426 of Curiosity's mission, meaning the rover had already survived more than 4,000 Martian days since landing inside Gale Crater in August 2012. That evening, Curiosity used its mast-cam cameras to record a sequence lasting about 16 minutes. The landscape below was moving deeper into twilight, but high overhead, thin clouds were still catching sunlight. Some appeared as faint reddish streaks. Others developed delicate green and blue edges. Beneath the highest clouds were pale streamers extending downward, almost as though something were falling from them. And something was. The highest portion of this cloud system was roughly 60 to 80 kilometers above Curiosity. That is far above the rover, far above Mount Sharp, rising from the center of Gale Crater, and high enough that the atmosphere is extraordinarily thin. The white streamers descending from the clouds appear to contain carbon dioxide ice particles falling toward lower altitudes. Some extend down toward roughly 50 kilometers above the surface. As those particles enter warmer layers of air, they disappear again, returning directly from solid carbon dioxide to gas. So what Curiosity was watching was not simply a colorful cloud moving across the sky. It was part of a complete atmospheric process. Martian air was becoming cold enough for its main gas to freeze into microscopic crystals. Those crystals were growing, some were beginning to fall, and then they were disappearing again before they could ever reach the ground. Mars can certainly freeze carbon dioxide. In fact, enormous quantities of it freeze onto the polar regions every Martian winter. But Gale Crater is close to the equator at roughly 5 degrees south latitude, and these particular high-altitude clouds were not expected to form there so readily. That distinction matters. Scientists are not saying the clouds violate any known law of physics. Carbon dioxide will freeze whenever pressure and temperature reach the right combination. The problem is that the Martian atmosphere above Gale was not expected to become cold enough, often enough, to produce what Curiosity keeps seeing. And it really does keep seeing it. The first recognized season of these unusual twilight clouds occurred in 2019. Curiosity saw them again during the corresponding season in 2021, then again in 2023, and once more in 2025. A Martian year lasts about 687 Earth days, so these observations are separated by complete cycles of Martian seasons. The clouds repeatedly return during early southern autumn. Researchers have now watched the pattern for long enough that the timing is becoming predictable. Instead of simply hoping that Curiosity happens to notice the clouds, the team can plan observations for the part of the Martian year when they expect them to return. That makes a random weather event increasingly difficult to use as an explanation. Whatever is cooling this part of the atmosphere appears to be connected to a larger seasonal process that repeats as Mars moves around its orbit. Yet the most immediately useful clues are still sitting inside the images themselves. The pinks, greens, and blues are not merely showing us that the clouds are beautiful. The exact way those colors appear can reveal something surprisingly specific about the microscopic crystals inside them. And that is where the photographs begin to function as measurements. Those colors give researchers something much more useful than a beautiful image. When Curiosity photographs pale red, orange, green, and blue bands along the edges of a cloud, the pattern reveals information about the tiny particles suspended inside it. The effect is called iridescence, and it appears when light interacts with many particles that are similar enough in size to scatter different wavelengths in an organized way. Visible light contains a range of wavelengths. Red light has a longer wavelength than blue light, with green and orange falling between them. When that light encounters particles only a few micrometers across, meaning only a few millionths of a meter, it can bend and spread around them. This process is called diffraction. The result depends strongly on particle size. If a cloud contains ice crystals with many different sizes, each group scatters light somewhat differently. Those overlapping effects tend to blend together, which helps explain why many ordinary clouds appear mostly white or gray. A cloud containing particles within a much narrower size range can preserve stronger color separation. One part of the cloud may develop a reddish edge, while another shifts through green and blue. That is what Curiosity has been seeing. Scientists use the word nacreous for especially vivid iridescent clouds. The word means mother of pearl, referring to the shifting pastel colors seen on the inside of some shells. On Earth, nacreous clouds are rare and usually associated with extremely cold regions of the stratosphere. On Mars, Curiosity provided the first images showing this kind of cloud iridescence on another planet. The clouds are also described as noctilucent. That word means night shining. They become visible around twilight because the rover and the ground below may already be entering darkness, while the much higher clouds are still receiving direct sunlight. Their altitude allows them to remain illuminated for a short time after the landscape beneath them has dimmed. During these observations, Curiosity captured more than colored fringes. Researchers also identified what is known as a scattering corona. A corona is a series of faint colored rings that can form around a bright source when light passes through a cloud made from particles with unusually similar sizes. On Earth, coronas are often seen around the Moon or occasionally around the Sun, produced by tiny water droplets or ice crystals. Curiosity recorded the first known Martian cloud corona. That matters because a corona requires a fairly orderly particle population. The crystals do not need to be exactly identical, but their sizes have to fall within a relatively narrow range. Researchers can compare the spacing and color of the rings with models of light scattering to estimate how large those particles are and how much their sizes vary. The same approach revealed something even more detailed inside individual Martian clouds. Different regions of the clouds showed different patterns of iridescence. That indicates that particle sizes were changing from one part of the cloud to another. The Curiosity observations, therefore, produced the first evidence of particle size variations within individual clouds on Mars. This gives scientists a way to watch cloud microphysics from the ground. Cloud microphysics simply means the small-scale processes that control how cloud particles form, grow, change size, and eventually fall. Curiosity cannot reach 60 or 70 kilometers into the atmosphere. It cannot collect one of these carbon dioxide crystals and place it inside an instrument. Its mast-cam cameras remain on the surface, looking upward from Gale Crater. Yet the light arriving at those cameras carries information from the particles themselves. Researchers can study where the colors appear, how they change through the cloud, and whether a corona forms. From that, they can begin estimating whether the particles formed at roughly the same time, whether some regions are growing faster than others, and how uniform the cloud remains as it develops. The colors were also probably visible without any scientific instrument. Researchers studying the observations concluded that a person standing beside Curiosity under the right twilight conditions could likely have seen at least some of the iridescence with their own eyes, although the actual clouds would have appeared faint against the darkening Martian sky. So the pastel bands recorded by Curiosity are doing several jobs at once. They reveal the presence of unusually uniform ice particles, show where particle sizes begin to differ, and provide a way to study cloud growth from tens of kilometers away. The photographs contain one more useful piece of geometry. Because these clouds remain illuminated after the ground below has entered shadow, the timing of that fading light can be used to work out how high above Mars they are. The timing of those colors provides a second measurement. Curiosity often sees the highest twilight clouds after the surface around Gale Crater has already begun to darken. The rover may be sitting in evening shadow, while thin clouds far overhead are still being struck by direct sunlight. That difference is possible because the cloud layer sits high enough above the surface to remain exposed to the last rays of the day. Mars rotates once every 24 hours and about 37 minutes. As evening advances, the boundary between daylight and darkness moves across the planet. Astronomers call that boundary the terminator. From the surface, the process can be pictured as the planet's shadow gradually rising through the atmosphere. Low terrain enters darkness first. Higher layers continue receiving sunlight for a little longer. Eventually, the shadow reaches them as well, and the clouds fade. That changing illumination gives researchers a way to estimate altitude. Curiosity's position inside Gale Crater is known very precisely. Scientists also know the rover's local time, the season, the angle of sunlight, and the position of Mars in its orbit. When a particular cloud structure remains illuminated for several minutes after the ground below has entered shadow, its height can be constrained using straightforward geometry. Researchers studying Curiosity's twilight observations tracked where the boundary between illuminated and shadowed cloud material moved through the images. A cloud entering darkness earlier had to be lower. A cloud remaining bright later had to be higher. The measurements place the thin, cirrus-like twilight clouds seen in these observations at roughly 50 to 80 kilometers above the Martian surface. Cirrus-like describes their appearance. They resemble the thin, wispy high clouds familiar from Earth, although the material inside them can be very different. The strongest evidence for carbon dioxide ice applies to the higher part of this system, roughly 60 to 80 kilometers above Gale. At those heights, the atmospheric pressure is extremely low, and temperatures can become cold enough under the right circumstances for gaseous carbon dioxide to freeze directly into solid crystals. Mars can also produce mesospheric clouds across an even broader range. The mesosphere is a high atmospheric region above most ordinary weather. Martian cloud observations and models place some mesospheric clouds between roughly 40 and 100 kilometers above the surface, depending on season, latitude, local temperature, and cloud composition. The Curiosity images also show lower structures with a different appearance. Some wave-like clouds sit below about 55 kilometers. These lower clouds are more consistent with water ice. During the January 2025 observations, faint, lower cloud layers around roughly 50 kilometers were visible beneath the higher carbon dioxide clouds. That separation matters because a photograph alone does not reveal composition with certainty. A pale cloud made from water ice and one made from carbon dioxide ice can both look white or faintly colored in a rover image. Researchers therefore combine several clues. Altitude helps because different materials condense under different atmospheric conditions. Temperature estimates narrow the possibilities further. The shape of the cloud, the way its particles scatter light, the season in which it appears, and the way material falls beneath it all contribute additional evidence. Taken together, those clues make the carbon dioxide interpretation much stronger for the highest twilight clouds. This is a useful example of how planetary science often works with limited tools. Curiosity does not carry a weather balloon that can climb 70 kilometers into the Martian atmosphere. It cannot fly an aircraft through the cloud layer or return an ice crystal to the surface. Instead, researchers use the rover's cameras, the known position of the planet, and the slow movement of evening shadow. A few minutes of fading light become a rough vertical ruler extending tens of kilometers above Gale Crater. Once those heights are established, the atmosphere begins to separate into distinct layers. Lower clouds can contain frozen water. Higher clouds can contain frozen carbon dioxide. Mars is capable of building both, and understanding the difference is essential to explaining why the clouds above Gale are so unusual. The two cloud layers above Gale Crater are made possible by a basic feature of the Martian atmosphere. Mars has more than one substance capable of freezing into clouds. On Earth, the word cloud usually brings water to mind. Tiny liquid droplets or ice crystals collect in the atmosphere after water vapor cools enough to condense. Mars can produce water ice clouds too, but water is only a trace component of its atmosphere. More than 95% of the Martian atmosphere is carbon dioxide. Nitrogen and argon make up most of what remains, while water vapor is present only in very small amounts that change with season and location. That difference in composition gives Mars an unusual kind of weather. Water ice clouds form when the small amount of atmospheric water vapor cools until it can freeze. The process often begins on microscopic dust particles already floating through the air. Those grains provide surfaces on which water molecules can collect and form ice crystals. Scientists call that process nucleation, meaning the first step in building a new solid particle. Mars provides plenty of dust for this to happen. Its surface is covered in fine mineral material that winds can lift kilometers into the atmosphere. Some particles remain suspended long enough to travel enormous distances before eventually settling again. Curiosity has photographed water ice clouds many times during its mission. In 2017, for example, the rover recorded thin, wispy clouds moving across the sky above Gale Crater. Their appearance resembled high cirrus clouds on Earth, and atmospheric models indicated that they were probably made from water ice. Other Curiosity images have shown faint fall streaks extending beneath water ice clouds. These form when crystals become large enough to begin descending. In the extremely dry Martian atmosphere, much of that falling ice can disappear before reaching the surface. The higher twilight clouds we have been following require a different set of conditions. Carbon dioxide can also freeze directly from gas into solid ice. On Earth, we normally encounter solid carbon dioxide as dry ice, produced industrially and kept at very low temperatures. On Mars, carbon dioxide is already the main gas in the atmosphere, so a sufficiently cold region of air can turn part of the atmosphere itself into ice particles. The required temperatures are much lower than those needed to form ordinary water ice clouds. That is why cloud altitude becomes so useful. Lower cloud structures can exist under conditions where water ice is stable. High in the Martian mesosphere, where temperatures can fall much farther, carbon dioxide ice becomes possible. Curiosity's January 2025 observations appear to show both kinds at the same time. The highest cloud structures, around 60 to 80 kilometers above the surface, include the iridescent features and falling plumes interpreted as carbon dioxide ice. Beneath them, around 50 kilometers high, much fainter cloud structures are more consistent with water ice. NASA's sequence shows another striking difference between those layers. The lower clouds appear to move in a different direction from the higher clouds. We will return to that motion later, because it reveals something about how Martian winds change with altitude. For now, the important point is that one twilight scene can contain two separate cloud systems, existing at different heights and under different temperatures. The physics behind both follows the same general rule. A gas reaches saturation when the local combination of temperature and pressure no longer allows all of it to remain in gaseous form. For water vapor, that threshold can produce water ice. For carbon dioxide, the atmosphere must become much colder before solid CO2 can form. This gives Mars a kind of weather that has no ordinary equivalent in Earth's lower atmosphere. Its thin air carries traces of water that can freeze onto dust, while its dominant atmospheric gas can also become part of the cloud system when conditions are cold enough. The high clouds above Gale therefore fit within known Martian physics. The unusual part is how often Gale appears to reach the temperatures needed to make them. Carbon dioxide freezing on Mars is already a familiar part of the planet's climate. Every Martian winter, large amounts of atmospheric carbon dioxide condense onto the polar regions as dry ice. The seasonal caps can spread across millions of square kilometers before warming temperatures cause that ice to return directly to gas during spring. Those polar deposits form because winter temperatures become extremely low for long periods. Gale Crater presents a very different environment. Gale sits close to the Martian equator, at about 5 degrees south latitude and 137 degrees east longitude. Curiosity has been exploring the crater since August 2012, several thousand kilometers from either pole. At this latitude, seasonal temperature changes are less extreme than they are in the polar regions. The high atmosphere above Gale can still become extremely cold. The important issue is whether it becomes cold enough for carbon dioxide to cross its frost point. A frost point is the temperature at which a gas begins changing directly into solid ice under a particular pressure. The exact temperature depends on pressure, so there is no single number that applies everywhere on Mars. As pressure decreases higher in the atmosphere, the condensation conditions also change. At roughly 60 to 80 kilometers above Gale, the air is extraordinarily thin. Carbon dioxide molecules are widely separated, and forming solid particles requires the local temperature to fall below the threshold appropriate for that pressure. A small temperature difference can therefore have a large physical effect. If a pocket of air remains a few degrees too warm, its carbon dioxide stays gaseous. If atmospheric motion cools that same pocket enough to cross the frost point, microscopic dry ice particles can begin forming. Researchers already knew that high-altitude carbon dioxide clouds were possible on Mars. Spacecraft had detected mesospheric CO2 clouds in other locations, and atmospheric models had identified regions where the necessary temperatures could occur. Gale Crater was a difficult place to fit into that picture. Models of the Martian middle atmosphere include much more than latitude. They have to account for the planet's mountains, craters, seasonal heating, atmospheric tides, and waves moving vertically through the air. Atmospheric tides are large pressure and temperature oscillations, driven mainly by the daily cycle of solar heating. They can move through the atmosphere across enormous distances. Gravity waves operate differently. They form when air is displaced upward or downward, and gravity tries to restore it to its original level. As those waves climb, rising portions of air can expand and cool. Both processes can create colder regions high above the surface. Earlier modeling suggested that Mars's topography strongly controls where these waves can reach the mesosphere. Some longitudes appeared much more favorable than others for producing the brief temperature drops needed for carbon dioxide clouds. Gale Crater, at 137 degrees east, was not among the clearest expected locations. That makes Curiosity's repeated observations useful for more than identifying an unusual cloud. The atmosphere is clearly finding a way to produce the required cold conditions over Gale. The measurements show that the threshold is being crossed. What remains uncertain is which combination of atmospheric tides, gravity waves, seasonal circulation, and local geography is producing that cooling so reliably. The phrase, "these clouds should not be here," therefore, has a very specific scientific meaning. The clouds follow ordinary physical laws. Carbon dioxide freezes when pressure and temperature allow it. The surprise comes from the atmospheric environment needed to reach those conditions at this place. Something represented imperfectly in current models appears to be lowering temperatures enough for dry ice crystals to form tens of kilometers above Curiosity. One isolated event could have been an unusually strong atmospheric disturbance that happened to pass over Gale at exactly the right time. Curiosity has instead watched the same kind of twilight clouds return across multiple Martian years during the same part of the planet's seasonal cycle. That regularity turns an unexpected cold pocket into a repeatable pattern. The timing of the clouds makes their appearance more revealing. Curiosity first recognized this unusual iridescent twilight phenomenon in 2019. During that season, the rover's cameras recorded thin, high-altitude clouds appearing shortly after sunset, with delicate pastel colors along parts of their edges. The same kind of clouds returned in 2021. They appeared again in 2023, and then once more in January 2025. Those dates may look like a simple pattern separated by 2 Earth years, but the more important interval is the Martian year. Mars takes about 687 Earth days to complete one orbit. That is almost twice the length of an Earth year. Each recurrence therefore represents another complete cycle of Martian seasons. The clouds are returning during early southern autumn. That seasonal timing is important because the Martian atmosphere changes substantially as the planet moves around its orbit. Different regions receive different amounts of solar heating. Temperatures shift. Large-scale circulation patterns reorganize. Atmospheric tides change strength, and waves moving upward through the atmosphere can behave differently from one season to another. Dust also follows seasonal patterns. During some parts of the Martian year, more dust is lifted from the surface and carried high into the atmosphere. That dust absorbs sunlight and changes how heat is distributed through the air, which can influence winds and temperature far above the ground. So, a repeated cloud season points toward a repeated atmospheric cause. Researchers now have more than the visible light photographs from Mastcam. Curiosity has also accumulated a long record of ultraviolet observations spanning about 5 Martian years. Ultraviolet photometry measures how much ultraviolet light reaches the rover from different parts of the sky. Thin clouds can alter that light even when they are difficult to see clearly in ordinary images. That record shows a consistent increase in cloud activity during early southern autumn. The pattern has become regular enough that the science team no longer depends entirely on chance. Mark Lemon, one of the researchers studying these clouds, has explained that the team can now anticipate when the twilight cloud season is likely to begin and schedule observations around it. That predictability changes the scientific value of the phenomenon. A single cloud observed on one evening could result from an unusual local disturbance. A sudden change in wind, an especially strong atmospheric wave, or a brief cold pocket might create conditions that rarely occur again. 4 recurring seasons tell a different story. The atmosphere above Gale Crater repeatedly enters a state that allows these high carbon dioxide ice clouds to form at roughly the same part of the Martian year. That means the process is connected to the larger seasonal behavior of Mars. The planet's axial tilt is about 25 degrees, close enough to Earth's tilt to give Mars recognizable seasons. But Mars follows a more elongated orbit, so the amount of solar energy reaching the planet changes more strongly over the year than it does on Earth. Southern seasons are especially affected. Mars is closer to the center of its orbit during southern summer and farther away during southern winter, producing strong seasonal contrasts in temperature and circulation. By early southern autumn, the atmosphere is moving away from the warmer conditions of southern summer. Temperatures in some regions begin dropping, pressure patterns shift, and the upper atmosphere responds to changing tides and wave activity. The clouds appear during that transition. Researchers still do not have a complete explanation for why those seasonal changes produce repeated carbon dioxide cloud formation over Gale. The regular timing does narrow the possibilities. Whatever cooling mechanism is involved must recur with the Martian seasonal cycle, and it must do so strongly enough to lower temperatures in the high atmosphere across multiple years. That long pattern becomes even more striking when placed beside the history of Martian cloud observations. Spacecraft had been seeing clouds on Mars for decades before Curiosity began recording these iridescent ones, and those earlier missions established what kinds of clouds scientists expected to find. The first surface photographs of Martian clouds came long before Curiosity began watching Gale Crater. In 1997, NASA's Mars Pathfinder mission landed in Ares Vallis, a broad outflow channel near the Martian equator. Pathfinder was designed primarily to study the surface and test new landing technology, but its cameras also recorded the sky. Near twilight, Pathfinder detected faint clouds high above the landscape. Researchers estimated some of them were roughly 16 kilometers above the surface and interpreted them as water ice clouds. Tiny amounts of Martian water vapor had frozen onto suspended dust particles, producing thin layers that could still catch sunlight after the ground had begun to darken. That observation established something important. Even Mars's extremely thin atmosphere could support regular cloud formation. Later missions expanded the picture. NASA's Opportunity rover, which landed in Meridiani Planum in January 2004, photographed wispy clouds moving overhead during its long mission. Opportunity remained active for more than 14 years, giving scientists repeated opportunities to watch how cloud cover changed with the seasons. The Phoenix lander added a different kind of observation after touching down near Mars's northern polar region in May 2008. Phoenix used a laser instrument called LiDAR, which sends pulses of light upward and measures what is reflected back. That allowed the mission to detect clouds even when they were difficult to see with a camera. Phoenix found water ice clouds forming several kilometers above the ground and also detected streaks of ice crystals falling beneath them. Some of that material appeared to descend toward the surface, providing direct evidence that Mars could produce precipitation from water ice clouds. Curiosity continued this long record after landing in Gale Crater in August 2012. By 2017, the rover had photographed delicate clouds moving through the Martian sky during the planet's cloudier seasons. Their thin, streaked appearance resembled cirrus clouds on Earth. Scientists concluded that many were probably made from water ice, formed when the small amount of water vapor in the atmosphere froze onto dust particles. For years, that basic picture made sense. Mars had water ice clouds. They appeared at predictable seasons, often as thin layers or streaks, and they fit reasonably well within atmospheric models. Then Curiosity began seeing something different. In 2019, the rover recorded an unusual twilight cloud season above Gale Crater. Some of the highest clouds showed visible iridescence, with pale reds, greens, and blues appearing along their edges. Their altitude and timing suggested that many of them were forming much higher than the more familiar water ice clouds. Those observations returned in later Martian years. By 2024, researchers had enough material to analyze the phenomenon in much greater detail. On November 29, 2024, a study published in Geophysical Research Letters brought several years of Curiosity observations together. The researchers examined the seasonal timing, the altitude of the clouds, their optical properties, and the way different structures changed through twilight. The analysis identified the first Martian nacreous clouds, the mother-of-pearl type of iridescent cloud we discussed earlier. It also reported the first known scattering corona in Martian clouds, along with the first evidence that particle sizes vary within individual clouds. The study placed the cirrus-like twilight clouds roughly 50 to 80 kilometers above the surface, and found that the highest structures, especially those around 60 to 80 kilometers, were most consistent with carbon dioxide ice. That transformed a sequence of unusual photographs into a defined atmospheric problem. Surface missions were especially valuable because they could keep watching the same sky from the same location over many years. Orbiters usually pass over a region at specific times dictated by their orbit. A rover can stay in place and observe twilight repeatedly as the seasons change. Curiosity had spent more than a decade doing exactly that. The result was a long enough record to show that the high iridescent clouds were seasonal, repeatable, and associated with a location where atmospheric models had not strongly predicted them. And that location turns out to matter almost as much as the clouds themselves. Gale Crater sits close to the Martian equator, at roughly 5 degrees south latitude and 137 degrees east longitude. That location matters because the atmosphere above Mars is strongly shaped by the terrain beneath it. Gale itself is an enormous impact basin, about 150 kilometers across. Rising from its center is Mount Sharp, officially called Aeolis Mons, a layered mountain more than 5 kilometers high from the crater floor. Curiosity has spent years climbing through its lower slopes, while the crater walls and central mountain continually influence the winds moving through the region. Air flowing across uneven terrain does not remain perfectly smooth. Crater rims, mountain slopes, valleys, and broad changes in elevation disturb the atmosphere and generate waves that can travel upward. Those disturbances can eventually affect air tens of kilometers above the surface. One important part of this process involves atmospheric tides. These are large-scale changes in pressure and temperature, driven mainly by the daily cycle of solar heating. As different parts of Mars warm and cool, the resulting pressure patterns move around the planet as broad atmospheric waves. Topography changes how those tides behave. A large mountain or deep basin can alter the timing and strength of pressure waves passing through the atmosphere. Those tides can then interact with smaller gravity waves, helping some move upward while weakening or blocking others. This becomes important high above Mars, in the region where Curiosity's carbon dioxide clouds appear. Earlier atmospheric modeling suggested that Martian topography creates strong differences in how efficiently gravity waves can reach the mesosphere. The mesosphere is the high layer of atmosphere where Curiosity's twilight clouds are forming, tens of kilometers above the surface. In some longitude bands, upward-moving waves should have an easier path. Modeling particularly favored regions near about 0 degrees east and around 270 degrees east for stronger vertical wave propagation under certain seasonal conditions. Gale Crater is nowhere near either of those longitudes. Curiosity is sitting at about 137 degrees east, in a region where the interaction between terrain and atmospheric tides was expected to make frequent mesospheric carbon dioxide clouds less likely. That expectation was also consistent with the earlier observational record. Before Curiosity began repeatedly seeing the high twilight clouds during early southern autumn, relatively few reports had identified mesospheric clouds in this part of Mars at that season. Yet Curiosity keeps seeing them. There is also evidence from nearby regions showing that the atmosphere can behave differently over surprisingly modest distances. NASA's InSight lander operated in Elysium Planitia, roughly 600 kilometers north of Curiosity. In 2019, InSight detected noctilucent clouds, meaning high clouds that remained illuminated after the surface had entered twilight. That placed another set of high-altitude clouds within the same broader part of Mars, although the exact composition and atmospheric conditions were not identical to the Curiosity observations. The comparison suggests that this region may contain local or regional atmospheric structures that simplified models have difficulty reproducing. Terrain can influence winds close to the ground. It can also alter pressure waves that extend through much of the atmosphere. Those waves then affect which disturbances survive as they travel upward. By the time the effect reaches 50, 60, or 70 kilometers above the surface, a feature such as a crater wall or mountain range may have indirectly changed the temperature of a layer of air far overhead. That gives Gale Crater an unusual role in this story. Curiosity is positioned inside a landscape capable of disturbing the atmosphere in complicated ways, yet the cloud-forming conditions seen above it appear more favorable than earlier models expected. Something is carrying enough energy upward, or reorganizing the atmosphere strongly enough to create pockets where temperatures fall below the carbon dioxide frost point. The leading candidate for producing those temporary cold regions is an atmospheric phenomenon that can begin near the surface and grow much stronger as it climbs. They are called gravity waves. Gravity waves are one of the leading ways scientists think that cold pockets could be forming so high above Gale Crater. The name can be misleading. Atmospheric gravity waves are different from the gravitational waves produced by events such as colliding black holes. These waves occur inside an atmosphere, where gravity and buoyancy control the motion of displaced air. Imagine a layer of Martian air moving across uneven terrain. Gale Crater contains steep walls, broad slopes, and Mount Sharp rising several kilometers above the crater floor. When air is forced upward by terrain or disturbed by changing winds, it can be pushed away from the altitude where it would normally settle. Buoyancy then begins restoring it. Air that has been lifted tends to sink back toward its original level. Momentum can carry it past that level, after which it rises again. The result is an oscillation, with air moving upward and downward while the disturbance travels through the atmosphere. Similar waves occur above mountains on Earth. They can produce long bands of clouds downwind from mountain ranges when rising portions of the wave cool enough for water vapor to condense. Mars provides a more extreme version because its atmosphere is so thin. Near the Martian surface, atmospheric pressure averages less than 1% of sea level pressure on Earth. Higher in the atmosphere, at 50 or 70 kilometers, the pressure is smaller still. As a parcel of air rises into those thinner surroundings, the pressure around it decreases. The rising parcel expands. Expansion requires energy, and that energy comes partly from the thermal motion of the gas. Its temperature therefore drops. This is called adiabatic cooling, meaning the air cools mainly because it expands, rather than because it transfers heat into its surroundings. The descending part of the wave behaves in the opposite way. Air moves into higher pressure, compresses, and warms. A gravity wave can therefore create alternating layers or pockets of warmer and colder air as it passes through the mesosphere. Those temperature differences can become surprisingly important. Carbon dioxide remains gaseous while the local temperature stays above its frost point. If the rising part of a wave lowers the temperature by enough degrees, the air can suddenly cross that threshold. A region that would otherwise contain only gaseous carbon dioxide can begin producing microscopic solid particles. That gives researchers a plausible route from the terrain far below Curiosity to the dry ice clouds tens of kilometers overhead. Martian topography can generate gravity waves near the surface. As those waves propagate upward, the decreasing atmospheric density allows their amplitudes to grow. A disturbance that begins relatively gently near a mountain or crater can have a much larger temperature effect by the time it reaches the mesosphere. Atmospheric tides can influence the process as well. Those large pressure and temperature oscillations, driven mainly by solar heating, change the background atmosphere through which gravity waves travel. At certain seasons and locations, tides can create conditions that allow particular waves to reach greater heights. In other circumstances, they can weaken or block them. Both processes can contribute to unusually low mesospheric temperatures. This fits several pieces of the Curiosity observations. The clouds form high above the surface. They appear during a recurring part of the Martian year. Their location seems connected to atmospheric behavior that varies with geography. The explanation remains incomplete. Researchers still need to understand why wave-driven cooling seems effective enough over Gale Crater to create recurring carbon dioxide clouds, while observations from places such as Jezero Crater have produced a different result. The exact strengths, directions, and vertical paths of Martian gravity waves are difficult to measure directly, especially 60 or 70 kilometers above the surface. For now, the waves provide a physically realistic way to create the missing cold. They can lift Martian air into lower pressure, cool it through expansion, and briefly push carbon dioxide across the threshold, where solid ice can begin to exist. Once that threshold is crossed, the problem changes scale completely. The atmosphere has become cold enough. Now, individual carbon dioxide molecules have to assemble into billions of microscopic crystals and grow into a visible cloud. Once a pocket of Martian air becomes cold enough for carbon dioxide ice to exist, the cloud still has to build itself from individual molecules. That process begins with nucleation. Nucleation is the first stage of forming a solid particle from a gas. A few molecules have to gather into a small cluster that is stable enough to survive instead of immediately breaking apart again. Once that tiny particle exists, additional molecules can join it and the crystal can begin to grow. Curiosity's twilight observations suggest that this process begins near sunset. That timing fits the changing temperature of the atmosphere. As direct solar heating fades, high-altitude air cools. If a gravity wave or atmospheric tide has already lowered the local temperature, the additional evening cooling can push a small region below the carbon dioxide frost point. The first ice particles then begin forming. With Martian water ice clouds, scientists know that airborne dust grains often act as nucleation sites. Water molecules collect on those microscopic mineral particles and freeze around them. Mars contains an enormous supply of fine dust, and spacecraft have observed it suspended high in the atmosphere. For these high carbon dioxide clouds, the exact nucleation process is less firmly established. The Curiosity observations show that the particles form and grow, but they do not directly identify what each crystal begins on. The important point is that the atmospheric conditions allow stable carbon dioxide ice particles to appear. The optical measurements suggest something interesting about those first particles. They begin within a fairly narrow range of sizes. That helps explain the iridescent colors Curiosity sees. When many particles form under similar conditions at roughly the same time, they can begin growing at similar rates. A patch of cloud may therefore contain large numbers of crystals whose diameters remain close to one another. As more gaseous carbon dioxide freezes onto their surfaces, the particles become larger. This stage is called condensation growth. Molecules from the surrounding gas collide with an existing ice crystal and become incorporated into it. The rate of growth depends on local temperature, pressure, and how much carbon dioxide is available above the saturation threshold. Different parts of a cloud can experience slightly different conditions. One region may remain colder for longer and allow its crystals to keep growing. A nearby region may warm sooner, slowing the process. Some particles may have started forming a little earlier than others. Those differences gradually broaden the range of particle sizes. The cloud's appearance changes with them. A young region containing unusually uniform particles can produce stronger, cleaner bands of iridescence. As the particles grow and their sizes become less uniform, the colored fringes can shift, weaken, or spread differently through the cloud. That gives Curiosity a way to follow a process happening tens of kilometers above the rover. The Mastcam cameras cannot resolve individual crystals. Each particle is far too small and far too distant. Instead, researchers infer their collective behavior from how sunlight is scattered through millions or billions of them at once. Eventually, the particles become large enough for gravity to matter more strongly. Mars has only about 38% of Earth's surface gravity, but even that weaker pull slowly draws ice particles downward through the thin atmosphere. Their motion is called sedimentation, the gradual settling of particles under gravity. In the Curiosity images, this appears as pale streaks hanging beneath some of the high clouds. Those streaks are the next stage in the cloud's short life cycle. The particles have moved beyond formation and growth and have begun to fall. So within a single twilight period, a cloud can pass through several measurable stages. Carbon dioxide begins freezing near sunset. The new crystals grow through continued condensation, and some eventually become large enough to descend. The same particles that create the pastel colors are changing while Curiosity watches. And because particle size controls those colors so strongly, the shifting iridescence gives researchers a way to follow that growth without ever touching the cloud itself. The colors become especially useful once the particles start changing size. Earlier, the iridescence told us that large numbers of crystals inside the cloud were similar enough in size to scatter light in an organized way. As those crystals grow, that size distribution begins to change, and the cloud's colors change with it. A narrow population of particle sizes can produce clear diffraction fringes. Red, orange, green, and blue appear in different places because each wavelength of visible light interacts slightly differently with the particles. If one region of the cloud contains crystals that formed at nearly the same time and experienced similar temperatures, those particles can remain close in size. The iridescence there may appear relatively clean and strongly separated. A neighboring region can have a different history. Perhaps nucleation began a little earlier. The air may have stayed below the carbon dioxide frost point for longer, allowing more material to accumulate on each crystal. Small differences like these create different particle sizes within the same cloud. Curiosity can see the result in the changing pattern of color. That made the observations unusually valuable because scientists could compare separate parts of a single cloud rather than treating the entire structure as one uniform layer. The 2024 analysis found evidence that particle sizes varied from place to place inside individual Martian clouds. It was the first time researchers had been able to identify that kind of internal particle size variation in a cloud on Mars. Another clue came from a feature called a scattering corona. A corona is a group of faint colored rings that can appear around a bright light source when that light passes through a cloud containing many particles of similar size. On Earth, people sometimes see coronas around the Moon when a thin layer of water droplets or ice crystals passes in front of it. The spacing and strength of those rings depend on particle size. A cloud filled with a very broad mixture of crystal sizes tends to blur the pattern. When the particles are much more uniform, the rings become easier to distinguish. Curiosity recorded the first known scattering corona in the Martian atmosphere. That observation reinforces the idea that at least some parts of these twilight clouds contain unusually orderly groups of ice particles. For a period during their development, large numbers of crystals appear to form and grow under conditions similar enough to keep their sizes close together. The effect does not last indefinitely. As the cloud evolves, some particles grow faster than others. Temperature and carbon dioxide concentration can vary across only a small distance. Crystals also begin moving vertically through the atmosphere, placing them in slightly different environments. The size distribution gradually spreads out. That evolution changes how the cloud scatters light, giving researchers a way to follow part of the growth process through ordinary images. It is a remarkably indirect measurement. The Mastcam cameras remain on the floor of Gale Crater. The particles being studied may be 70 kilometers overhead and far too small for the cameras to resolve individually. Yet their collective effect on sunlight allows scientists to infer changes occurring at microscopic scales. Researchers still need many more observations before they can turn those colors into a precise clock for cloud development. The available sample is too small to determine exactly how quickly the carbon dioxide crystals grow, how long they remain suspended, or how rapidly their sizes diverge as the cloud matures. Reliable sedimentation timescales also require observations of more clouds through more complete portions of their life cycles. For now, the important advance is the measurement method itself. A faint band of color can reveal whether particles are unusually uniform. Differences across that band can show that one part of the cloud has developed differently from another. A corona can provide another check on the same microscopic structure. And once those crystals continue growing, the optical clues begin to give way to something much easier to see. Gravity starts pulling the largest particles downward, producing long pale streaks beneath the clouds. The pale streaks hanging beneath some of Curiosity's highest twilight clouds are the next visible stage of that particle growth. They resemble precipitation beneath clouds on Earth, where falling rain or ice can form long vertical trails. On Mars, the material in these particular high-altitude streaks appears to be carbon dioxide ice. The process begins in the cloud layer roughly 60 to 80 kilometers above the surface. As the microscopic crystals grow, gravity gradually pulls them downward. Mars has only about 38% of Earth's surface gravity, so the settling is weaker than it would be here, but the particles still descend through the atmosphere. Scientists call this gravitational sedimentation. The Martian atmosphere is also extremely thin, especially at those heights. There are far fewer gas molecules available to slow a particle as it falls. Even so, the crystals remain tiny enough that their descent is gradual rather than resembling large chunks of dry ice dropping through the sky. In Curiosity's twilight imagery, the falling material appears as narrow whitish plumes stretching below the main cloud deck. Some of those plumes can be traced downward toward roughly 50 kilometers above the Martian surface. That change in altitude matters because the atmospheric conditions change with it. The carbon dioxide crystals formed high above Gale, where the air became cold enough for solid CO2 to remain stable. As the particles descend, they enter layers where the temperature is higher. Eventually, the surrounding air becomes too warm for solid carbon dioxide to survive at the local pressure. The particles then begin to sublimate. Sublimation is the direct change from a solid into a gas. The ice does not need to melt into a liquid first. A carbon dioxide crystal simply absorbs enough energy for its molecules to leave the solid structure and return to the surrounding atmosphere. This is the same basic behavior seen when dry ice is placed in warmer conditions on Earth. Instead of producing a puddle, the solid gradually disappears as carbon dioxide gas escapes from its surface. Something similar happens high above Mars. A crystal forms near 70 kilometers altitude, grows inside the cold cloud, and begins falling. Several kilometers lower, it reaches warmer air. Its surface starts disappearing molecule by molecule until the particle is gone. The precipitation, therefore, has a limited vertical range. The observed carbon dioxide fall streaks do not need to approach the ground. Their visible life can begin around 60 to 80 kilometers high and end near roughly 50 kilometers, still far above Curiosity. Mars produces similar-looking structures in water ice clouds as well. When water ice particles grow large enough to fall, cameras and other instruments can sometimes detect streaks beneath the cloud layer. NASA's Phoenix lander observed water ice precipitation in the northern polar region during 2008, and Curiosity has photographed water ice fall streaks above Gale. The material differs, but the visual result can be similar. Small ice particles descend beneath a cloud and gradually disappear as they enter conditions where that solid phase can no longer persist. For the carbon dioxide clouds, the entire process can occur without anything reaching the Martian surface. Gas becomes solid high in the atmosphere. The particles grow while suspended inside the cloud, then drift downward through colder and warmer layers until sublimation returns them to gas. A complete precipitation cycle can therefore happen entirely in the sky. That gives the January 2025 sequence a particularly unusual structure. High above Gale are iridescent carbon dioxide clouds. Beneath them are pale falling plumes. Lower still, another cloud layer is visible around 50 kilometers altitude. Those lower clouds appear to be made from water ice. They also move differently from the cloud structures above them, revealing that the Martian atmosphere is divided into wind layers that can travel in very different directions at the same time. The lower cloud layer in Curiosity's 2025 twilight sequence adds another piece to the atmosphere above Gale Crater. Beneath the high iridescent clouds, researchers can see much fainter structures at around 50 kilometers altitude. These lower clouds are interpreted as water ice rather than carbon dioxide ice, because they occupy a warmer part of the atmosphere where water ice clouds are more likely to remain stable. The height difference is substantial. The likely carbon dioxide clouds sit roughly 60 to 80 kilometers above the surface. The lower water ice structures appear around 50 kilometers high. That places two separate cloud systems within the same stretch of Martian sky, separated by perhaps 10 to 30 kilometers of atmosphere. Their motion makes the distinction even clearer. NASA's analysis of the January 2025 sequence reports that the lower clouds appear to move in the opposite direction from the higher cloud structures. That can happen because wind on Mars changes with altitude. A wind speed or direction measured near the surface does not necessarily describe the air tens of kilometers overhead. Different atmospheric layers experience different pressure gradients and temperature differences, and those differences determine how air moves horizontally. Scientists call a change in wind speed or direction with height vertical wind shear. Vertical wind shear is common on Earth. An aircraft can take off into a surface wind, moving one way, and later encounter much stronger winds flowing in a different direction several kilometers higher. Mars can produce the same general effect, although the atmosphere is far thinner and the circulation is shaped by a very different climate. At Gale, the lower water ice clouds may be carried by one circulation pattern while the higher carbon dioxide clouds move with another. Temperature plays a major role. Air flows, partly because pressure varies from place to place. Heating produces expansion and changes pressure. Cooling changes density and can shift those gradients. Since Mars absorbs solar energy differently at the surface, in dusty layers, and high in the atmosphere, the forces controlling the wind can change substantially with altitude. Atmospheric tides add another layer of motion. These large pressure waves travel through the Martian atmosphere as daily heating shifts around the planet. Gravity waves can move through them at the same time, sometimes strengthening or weakening as they climb. The result is a vertically layered atmosphere. A cloud around 50 kilometers high can be carried eastward, while another 20 kilometers above it moves westward. Their temperatures can differ enough for one layer to support water ice, while the other supports frozen carbon dioxide. This helps explain why a single twilight photograph can contain so much information. The high iridescent clouds reveal extremely cold conditions in the mesosphere. Their falling plumes show ice particles descending into warmer air. The lower clouds reveal a second circulation regime beneath them. Curiosity is effectively looking through several moving layers at once. That also makes the larger mystery harder to reduce to one simple seasonal wind pattern. If the atmosphere over Gale were responding in the same way everywhere on Mars, similar high carbon dioxide clouds should appear more consistently at other rover sites during the same season. NASA has another rover with cameras pointed at the Martian sky. Perseverance has been operating inside Jezero Crater since 2021, and it has not seen the same carbon dioxide twilight clouds that Curiosity keeps finding above Gale. Perseverance gives scientists a useful comparison because it is watching a different part of Mars under many of the same broad seasonal cycles. Curiosity landed inside Gale Crater in August 2012. Perseverance arrived in Jezero Crater in February 2021, more than 3,000 kilometers away. Jezero sits farther north, near 18 degrees north latitude. It is also an ancient impact basin, roughly 45 kilometers across, with a preserved river delta on its western side. Perseverance was sent there mainly to study the geology of an ancient lake environment and search for signs of past habitability, but its cameras also record clouds and other atmospheric activity. Those observations have produced an important absence. NASA reports that Perseverance has not detected carbon dioxide ice twilight clouds comparable to the iridescent high clouds. Curiosity repeatedly sees above Gale. That does not mean Jezero has no clouds. Perseverance has photographed Martian clouds, including water ice clouds. The difference involves the particular high-altitude carbon dioxide cloud season that has become so familiar at Gale. If latitude alone controlled the phenomenon, the comparison might be relatively simple. Mars has strong seasonal changes with latitude, so one region could naturally become colder than another. Other surface missions make that explanation less satisfying. Mars Pathfinder landed in Ares Vallis in 1997, near the equatorial region, and observed twilight clouds from the surface. More than 2 decades later, NASA's InSight lander operated in Elysium Planitia, roughly 600 kilometers north of Curiosity, and detected noctilucent clouds in 2019. Those locations show that high twilight clouds are not confined to one simple latitude band. The differences between the sites bring several geographic variables into play at once. Longitude matters because global atmospheric tides do not behave identically around the entire planet. Terrain matters because crater rims, volcanic provinces, mountain slopes, and broad changes in elevation can generate or redirect waves. Seasonal circulation changes the background winds through which those waves travel. Altitude also matters. A disturbance that reaches 50 kilometers may affect water ice clouds without producing the colder conditions required for carbon dioxide ice around 70 kilometers. A wave that continues higher can produce a very different cloud environment. Local atmospheric structure can therefore determine whether a particular region crosses the carbon dioxide frost point at the right altitude and time of year. This is why Gale and Jezero are such a useful pair. Both contain active NASA rovers. Both provide repeated surface observations across changing seasons. Their skies, however, are sampling different combinations of terrain and atmospheric circulation. Researchers suspect that some regions of Mars may be naturally predisposed to producing these high carbon dioxide twilight clouds. That idea remains a hypothesis. Scientists do not yet have enough surface stations distributed across Mars to map the phenomenon in detail. At the moment, the observational network consists of a small number of landing sites, separated by hundreds or thousands of kilometers. Earth meteorology relies on thousands of weather stations, balloons, aircraft, satellites, and ocean instruments. Mars has only a handful of surface locations where instruments have watched the atmosphere continuously for meaningful lengths of time. A regional pattern can therefore remain hidden for years simply because no spacecraft happens to be standing beneath it. The contrast between Curiosity and Perseverance suggests that the Martian atmosphere contains localized regimes that our present network is only beginning to reveal. Gale repeatedly develops conditions favorable for high carbon dioxide clouds. Jezero has not shown the same pattern. Pathfinder and InSight add still more geographic variation. Connecting those scattered observations requires a mechanism large enough to link season and location while still responding to local terrain. Mars has exactly that kind of mechanism in the form of atmospheric tides, enormous pressure and temperature waves that move around the planet every day. Curiosity has been measuring these larger atmospheric motions from the floor of Gale Crater since shortly after it landed. Mounted on the rover is the Rover Environmental Monitoring Station, usually shortened to REMS. Its sensors track conditions including air temperature, ground temperature, wind, humidity, ultraviolet radiation, and atmospheric pressure. The pressure measurements reveal that Mars breathes in a remarkably regular daily rhythm. At Gale Crater, surface pressure can change by around 10% over the course of a single Martian day. For an atmosphere already less than 1% as dense as Earth's at sea level, that is a substantial variation. Early REMS observations showed a repeating pattern in which pressure often reached a high point at around 7 in the morning and fell toward a minimum near 4 in the afternoon. Those daily changes are partly produced by thermal atmospheric tides. The word tide here describes enormous waves of pressure and temperature moving through the atmosphere. Their main source is the daily cycle of solar heating. As daylight reaches the Martian surface, the ground warms. That heat is transferred into the thin air directly above it. Different regions heat at different rates because Mars contains dark plains, bright dusty surfaces, deep craters, and enormous elevation changes. The uneven heating creates differences in atmospheric pressure. Those pressure differences begin driving motion through the air. Because Mars rotates once every 24 hours and about 37 minutes, the heating pattern continually moves around the planet. The resulting pressure waves can travel enormous distances and repeat with periods tied to the Martian day. Some complete one cycle each sol. Others can complete 2 or more cycles during the same period. These thermal tides affect much more than the pressure recorded by Curiosity near the ground. As the waves travel upward, they can alter temperatures and winds through large portions of the atmosphere. Their behavior also depends on the terrain below. Gale Crater is a particularly complicated setting. Its floor lies inside a deep impact basin, while Mount Sharp rises several kilometers from the center. Beyond Gale are larger regional changes in elevation that influence how atmospheric waves move across Mars. Topography can distort a thermal tide as it passes. A pressure wave traveling over high terrain may behave differently from the same wave crossing a broad lowland. Those differences can change which parts of the wave continue upward into the mesosphere. That creates an important connection to the gravity waves we discussed earlier. Gravity waves can rise from disturbances associated with terrain or changing airflow. Thermal tides create a moving background of pressure, temperature, and wind through which those smaller waves must travel. At some times and places, that background can help a gravity wave reach higher altitudes. Under different conditions, the wave may weaken before it gets there. The interaction can alter temperatures 60 or 70 kilometers above the surface. That means the cold pocket responsible for a tiny iridescent cloud above Gale may depend partly on a pressure wave extending across a large fraction of Mars. Curiosity sees the local result. Its weather station measures the pressure rising and falling at the surface. Its cameras then look upward and sometimes find carbon dioxide ice forming in the high atmosphere during a particular season. The two observations occur on vastly different scales, yet they belong to the same connected system. Mars's atmosphere is tenuous, but it still supports global tides, vertically propagating waves, and layered circulation capable of changing temperatures high above the ground, and its pressure changes on an even larger seasonal scale. Over the course of a Martian year, a significant fraction of the atmosphere itself freezes onto the polar caps and later returns to the air. The seasonal pressure record from Curiosity shows that the atmosphere above Gale Crater changes on a much larger scale than the daily thermal tide. Over the course of a Martian year, pressure rises and falls as enormous amounts of carbon dioxide move between the atmosphere and the surface. During winter, temperatures near each pole become cold enough for atmospheric carbon dioxide to freeze directly onto the ground. The gas forms a seasonal layer of dry ice across the polar regions. This removes carbon dioxide from the atmosphere. As more gas freezes out, the total mass of the atmosphere decreases and surface pressure falls across the planet. Curiosity can detect that change from Gale Crater, even though the seasonal ice is forming thousands of kilometers away. When spring returns to a pole, Increasing solar heating warms the frozen carbon dioxide. The dry ice then sublimates, changing directly from solid back into gas. That carbon dioxide re-enters the atmosphere, increasing its mass and raising pressure again. The scale of this cycle is remarkable. Over a Martian year, roughly 30% of the atmosphere's mass can move in and out of the seasonal polar caps. On Earth, weather can redistribute water between the atmosphere, oceans, snowfields, and ice sheets. The main gases in Earth's atmosphere remain gaseous through ordinary seasonal changes. Mars operates differently because carbon dioxide is both the dominant atmospheric gas and a substance that can freeze under natural surface conditions. For several months at a time, part of the atmosphere becomes part of the landscape. Curiosity's pressure sensor has recorded the consequences directly. As the seasonal caps grow and retreat, the rover measures the global pressure response from inside Gale Crater. The two hemispheres do not behave identically. Mars follows a noticeably elliptical orbit, meaning its distance from the Sun changes more during a year than Earth's does. Southern summer occurs when Mars is relatively close to the Sun, while southern winter occurs farther away. That makes southern seasons shorter and more intense in some respects, while northern seasons are longer and milder. The seasonal carbon dioxide caps therefore grow and retreat differently at the two poles. Their timing, extent, and contribution to atmospheric pressure reflect the unequal heating produced by Mars's orbit. This creates a planet-wide exchange of mass. Carbon dioxide freezes onto a polar surface. Months later, that same material returns to the atmosphere and can be carried elsewhere by global circulation. The process repeats every Martian year, which lasts about 687 Earth days. Seen at this scale, the high clouds above Gale begin to look less isolated. A microscopic carbon dioxide crystal forming 70 kilometers above Curiosity and a seasonal polar cap covering an enormous region of the planet are governed by the same basic phase change. Both appear when pressure and temperature allow gaseous carbon dioxide to become solid. The difference is scale. At the poles, the process can remove a huge fraction of the atmosphere and store it temporarily on the ground. Above Gale, the same substance freezes into tiny particles that may survive for only a short time before falling and sublimating. That gives Mars one of the strangest climate systems in the solar system. Its principal atmospheric gas regularly shifts between air, cloud ice, and seasonal surface deposits. Carbon dioxide provides most of the mass in that system, but it does not operate alone. Two other materials strongly influence how heat and moisture move through the Martian atmosphere: dust and water. The fine reddish dust that gives Mars much of its familiar color is constantly moving through the atmosphere. Winds lift loose particles from the surface, and dust devils can pull them upward in narrow rotating columns. Once airborne, the smallest grains can remain suspended for long periods and travel horizontally with large-scale winds before gravity eventually brings them back down. That dust does more than tint the sky. It also helps Martian water ice clouds form. Water vapor in the Martian atmosphere is scarce, and individual water molecules usually need a surface on which to begin freezing. Microscopic dust grains provide that surface. A tiny mineral particle can act as an ice nucleus, meaning the central seed around which water molecules collect and freeze. Many Martian water ice cloud particles therefore contain dust at their centers. This creates a direct physical connection between the surface and the clouds above it. A grain lifted from the ground can be carried kilometers upward, become coated in water ice, spend time inside a cloud, and later descend again as the ice particle settles. Dust also changes atmospheric temperature. Airborne particles absorb some incoming solar radiation and scatter some of it in other directions. They can also absorb infrared radiation coming from the warmer surface below. The effect depends on how much dust is present, how high it reaches, and the size of the particles. During dusty periods, the atmosphere can warm at some altitudes because suspended grains absorb radiation directly. At the same time, less sunlight may reach the ground, allowing the surface beneath the dust to cool. Those temperature changes alter pressure gradients. A pressure gradient is simply a difference in atmospheric pressure from one place to another. Air tends to move in response to those differences, so changing the way Mars is heated can change the winds. Those winds then control where more dust is lifted and where existing dust is transported. Clouds become part of the same feedback. When water ice forms around dust grains, some of those particles can eventually become large enough to settle. In that way, cloud formation can help remove dust from parts of the atmosphere. The clouds also interact with radiation themselves. A thin water ice cloud, high above the surface, may affect incoming and outgoing energy differently from a thicker cloud at a lower altitude. Depending on its height, particle size, and optical thickness, meaning how strongly it blocks or redirects light, a cloud can warm one region of the atmosphere while cooling another. That matters for circulation. Modern Mars climate models increasingly treat water ice clouds as radiatively active rather than passive collections of particles. Their interaction with sunlight and infrared radiation can change temperature patterns enough to alter large-scale winds. Those changed winds can then affect dust lifting at the surface. The result is a coupled system. Dust influences cloud formation and atmospheric heating. Clouds change the temperature structure and can remove some dust through sedimentation. The altered temperature field changes winds, which redistribute dust and water vapor across the planet. NASA's Mars Climate Modeling Center has used increasingly detailed computer simulations to study these interactions. When radiative effects from water ice clouds are included, the predicted circulation can shift noticeably, and the locations where models expect dust to be lifted can change as well. That is important because even small adjustments can propagate through the climate system. A little more dust at one altitude can change heating. That can alter winds several kilometers away. Those winds can carry water vapor into a region where new clouds form. Mars therefore contains several overlapping cycles operating at once. Carbon dioxide moves between the atmosphere and the polar caps on a planetary scale. Dust moves between the surface and the air. Water moves in much smaller quantities through vapor, ice clouds, frost, and buried reservoirs. Curiosity is watching all of this from a place where the contrast with the past is especially striking. Modern Gale Crater is cold and dry, with only tiny amounts of water moving through its atmosphere. The rocks beneath the rover record a time when liquid water remained on the surface long enough to build lakes and leave hundreds of meters of sediment behind. The rocks directly beneath Curiosity preserve a record of a much wetter Gale Crater. More than 3 billion years ago, this basin contained lakes. Water collected on the crater floor, deposited fine sediment, and then sometimes retreated as conditions changed. Evidence gathered during Curiosity's long climb through Gale suggests that this cycle of filling and drying happened repeatedly over extended periods rather than during one brief flood. Sedimentary rock records those environments because particles carried by water settle in layers. Fine mud can accumulate on a lake bottom grain by grain. Minerals forming in the water become trapped within the sediment, while chemical reactions leave traces of the temperature, acidity, and composition of the environment. Curiosity has encountered approximately 304 meters, about 1,000 feet, of sediment interpreted as material deposited in ancient lakes. That is a substantial thickness. Building hundreds of meters of lake sediment requires repeated deposition. Water carried material into Gale. Fine particles settled through the lake, and new layers accumulated above older ones. Later burial compressed those sediments into rock. Some of Curiosity's most important early discoveries came from a place called Yellowknife Bay. The rover reached Yellowknife Bay during its first Martian year on the surface and drilled into a fine-grained rock known as mudstone. Mudstone forms when very small sediment particles are deposited and later harden together. Curiosity examined a layer called the sheep bed mudstone. Samples drilled there contained clay minerals, making up roughly 20% of the material studied. Clay is particularly useful to planetary scientists because it usually forms through interactions between rock and liquid water. The type of clay and the surrounding chemistry can provide clues about what that water was like. At Yellowknife Bay, the evidence pointed toward water with a roughly neutral pH and relatively low salinity. Neutral pH means the water was neither strongly acidic nor strongly alkaline. Low salinity means it contained fewer dissolved salts than some of the harsher ancient environments identified elsewhere on Mars. The rocks also preserved different oxidation states of sulfur and iron. An oxidation state describes how electrons are distributed within an element. When both more oxidized and more reduced forms are available in the same environment, microorganisms can potentially use the chemical difference between them as an energy source. Curiosity also detected several elements considered important for life as we know it. These included carbon, hydrogen, oxygen, sulfur, nitrogen, and phosphorus. Together, those elements are involved in familiar biological molecules on Earth, from proteins and genetic material to cell membranes and energy-carrying compounds. Their presence does not demonstrate that organisms lived in Gale Crater. What the Yellowknife Bay findings establish is habitability. Habitability means an environment possessed conditions that could have supported life. Liquid water was present. The chemistry was relatively mild. Biologically useful elements and possible sources of chemical energy were available. Evidence of life would require an additional step, such as a convincing biological structure, chemical pattern, or other signature that could not be explained adequately by non-living processes. Curiosity has not established that ancient organisms inhabited Gale. It has established that at least some ancient Gale environments offered many of the ingredients microbial life on Earth requires. The contrast with modern Gale is difficult to miss. Today, Curiosity sits beneath an atmosphere so thin that surface liquid water is generally unstable for long periods. High overhead, carbon dioxide can freeze into microscopic crystals and disappear again before those crystals descend very far. Beneath the rover are rocks formed in lakes. Those two environments occupy the same crater at different points in Martian history. For Gale to sustain persistent surface water more than 3 billion years ago, its climate had to differ substantially from the cold, dry conditions Curiosity experiences today. A major part of that transformation involved the atmosphere itself. Over immense spans of time, Mars lost much of the gaseous envelope that once helped shape conditions at its surface. The ancient lakes recorded beneath Curiosity require a Martian climate very different from the one that exists today. Modern Mars has an atmosphere so thin and surface temperatures generally so low that stable liquid water cannot persist across the surface for long periods. Part of the explanation is that Mars gradually lost a large amount of its atmosphere to space. Early in the planet's history, Mars possessed a global magnetic field generated inside its interior. That field eventually disappeared as the planet cooled and its internal dynamo shut down. Without a strong global magnetic shield, The upper atmosphere became more directly exposed to conditions flowing outward from the sun. Ultraviolet radiation can break atmospheric molecules apart. The solar wind, a stream of charged particles moving outward through the solar system, can interact with the upper atmosphere and accelerate particles. Energetic solar storms can intensify those interactions. Over billions of years, several escape processes have removed atmospheric material. For a particle to escape permanently, it must gain enough energy to overcome Mars's gravity. Some ions, meaning electrically charged atoms or molecules, can be accelerated directly by electric and magnetic fields. Neutral particles can also escape, after collisions transfer enough energy to them. One important process is called sputtering. Sputtering begins when energetic charged particles strike the upper Martian atmosphere at high speed. Their collisions transfer energy to neutral atoms and molecules. Some of those neutral particles receive enough of a kick to fly upward and escape into space. The process happens one particle at a time, but over geological time the losses accumulate. NASA sent a spacecraft specifically to understand this kind of atmospheric erosion. The Mars Atmosphere and Volatile Evolution Mission, better known as MAVEN, launched on November 18, 2013. After a journey of about 10 months, it entered orbit around Mars on September 21, 2014. Its central goal was to study the Martian upper atmosphere and determine how gases escape into space, helping scientists reconstruct how the planet's climate changed over time. For years, researchers had indirect evidence that sputtering had occurred. A major breakthrough came in May 2025. Using MAVEN, scientists reported the first direct observation of atmospheric sputtering at Mars. Detecting it required several instruments to work together at the same time. The solar wind ion analyzer measured incoming charged particles. The magnetometer measured the surrounding magnetic field. The neutral gas and ion mass spectrometer measured particles in the upper atmosphere. Together, those measurements allowed researchers to connect energetic particles striking Mars with neutral atmospheric material being knocked upward. Under the observed conditions, the sputtering rate was roughly 4 times higher than earlier predictions. The measurements also showed that sputtering becomes stronger during solar storms when Mars is exposed to more intense flows of energetic particles. That result matters most when projected backward in time. The young sun was considerably more active than it is today. Mars would have experienced stronger ultraviolet radiation and more energetic solar conditions while its atmosphere was evolving. Atmospheric escape, therefore, provides a mechanism capable of gradually transforming the planet. As gases were removed, atmospheric pressure declined. Lower pressure made stable surface liquid water increasingly difficult to maintain. The lakes that once occupied Gale Crater eventually became part of the geological record beneath Curiosity. MAVEN spent more than 11 years studying that transformation from orbit. Contact with the spacecraft was lost on December 6, 2025. After months of attempts to recover it and analysis of its likely condition, NASA formally declared the mission ended on June 3, 2026. Its measurements leave scientists with a much clearer picture of atmospheric escape, including the first direct view of sputtering in action. The thin atmosphere surrounding Mars today is therefore the surviving product of a very long history, and reconstructing that history depends heavily on climate models. Those models must explain ancient lakes, atmospheric loss, and the modern environment Curiosity measures today. The strange carbon dioxide clouds above Gale reveal that even the present-day atmosphere still contains behavior those models do not fully reproduce. The carbon dioxide clouds above Gale Crater bring the story back to the present. Scientists use Mars general circulation models to simulate the planet's atmosphere. These are large computer models that divide Mars into a three-dimensional grid and calculate how air moves and changes through time. A useful model has to reproduce much more than an average temperature. It needs to generate realistic pressure changes and winds. It must move dust and water vapor through the atmosphere in plausible ways. It also has to account for cloud formation, atmospheric tides, and the smaller waves that can carry energy upward through different layers. Those processes interact continuously. Dust absorbs and scatters radiation, changing atmospheric temperature. Water ice clouds can also alter heating and circulation. Large thermal tides reshape pressure and wind patterns over the course of a Martian day. Gravity waves add another layer of complexity. Most global climate models cannot calculate every individual gravity wave directly, because many of those waves are far smaller than the model's grid cells. Instead, scientists use a process called parameterization. A parameterization is a simplified mathematical representation of a process that is too small or too complicated to simulate in full detail. The model estimates how gravity waves should transfer momentum and energy through the atmosphere based on the conditions it can resolve. That approximation can become important at 60 or 70 kilometers altitude. If a model underestimates how strongly a wave cools a region above Gale Crater, the simulated temperature may remain only a few degrees too warm. For many atmospheric measurements, a small error like that might appear modest. For carbon dioxide cloud formation, it can completely change the result. Carbon dioxide remains gaseous until local pressure and temperature cross the frost point threshold. Once that line is crossed, solid ice can begin to form. That makes these clouds unusually sharp tests of a climate model. Reality is showing that the atmosphere above Gale repeatedly becomes cold enough to produce carbon dioxide ice during early southern autumn. A model that repeatedly fails to reach that threshold at the same location and season is missing some part of the real temperature or circulation structure. The geographic distribution adds another constraint. Curiosity sees recurring high carbon dioxide clouds above Gale, while Perseverance has not observed comparable clouds above Jezero. Pathfinder and Insight add observations from still other locations. A strong model should eventually reproduce those regional differences, as well as the broader seasonal pattern. The particle measurements provide another test at a much smaller scale. Cloud microphysics describes how individual particles nucleate, grow, change size, and settle. Curiosity's iridescent colors and scattering corona indicate unusually narrow particle size distributions in some cloud regions, along with measurable differences from one part of a cloud to another. A model that produces a cloud at the correct altitude but gives its particles the wrong growth behavior would still be incomplete. Confidence increases when one atmospheric model can reproduce several independent observations at the same time. It should place clouds at realistic altitudes, produce them during the proper season, match their geographic distribution, and create temperature and wind structures consistent with measurements from the surface. That matters for ancient Mars because many of the same physical rules appear in simulations of the planet's past. Researchers reconstruct older climates using the physics of radiation, circulation, aerosols such as dust, and phase changes involving water and carbon dioxide. They then test whether a proposed ancient atmosphere could produce temperatures and precipitation consistent with the geological record. The rainbow clouds above Gale do not demonstrate that ancient Mars was warm or wet. They also provide no evidence that organisms lived there. Their value is more precise. They reveal a modern atmospheric process that current models do not yet reproduce completely. Improving that process gives scientists better constraints on the same physical machinery used when they calculate climates from billions of years ago. A cloud that may remain visible for only minutes at twilight can therefore influence how confidently researchers interpret an ancient lakebed beneath the rover. And because the mystery produces measurable predictions, scientists now have several ways to test what is actually causing it. The leading explanation still begins with gravity wave cooling, but several parts of the pattern remain unresolved. Researchers need to explain why the upper atmosphere over Gale Crater becomes cold enough for carbon dioxide ice, why the phenomenon returns during early southern autumn, and why the same kind of twilight clouds have not appeared over Jezero Crater in Perseverance's observations. More curiosity campaigns can help separate stable behavior from coincidence. If the rover continues imaging twilight clouds during future Martian years, scientists can compare the exact timing of each season. They can measure when the first clouds appear, how long the active period lasts, and whether the clouds reach similar altitudes each time. Repeated observations can also improve the particle measurements. The current sample is still too small to determine reliable growth and sedimentation timescales. Researchers need more clouds, observed through enough of their development, to estimate how quickly the carbon dioxide particles grow and how long they remain suspended before beginning to fall. The changing iridescence can provide part of that record. If particle size distributions evolve in a similar way from one cloud season to another, that would support a repeatable microphysical process. Larger variations could indicate that local temperature or wave strength changes considerably between Martian years. Geography may be even more important. Curiosity provides repeated observations from Gale Crater. Perseverance supplies a comparison from Jezero. Orbiting spacecraft can observe much larger portions of Mars and help place those two rover sites within the surrounding atmospheric environment. That combination can eventually produce geographic maps showing where high mesospheric clouds occur and where they consistently fail to appear. An absence can be valuable data. If Perseverance repeatedly watches the correct season and still does not see comparable carbon dioxide clouds, that places a useful limit on any explanation. A model cannot simply produce the clouds everywhere at similar latitudes and still match reality. The atmospheric measurements needed to test those models cover several scales. Temperature profiles would show whether the mesosphere actually reaches the carbon dioxide frost point. Wind measurements could reveal the background circulation through which gravity waves travel. Dust abundance matters, because dust changes atmospheric heating. Cloud altitude and particle size provide additional checks on what happens after condensation begins. Regional topography must be included as well. Crater walls, mountains, and broad changes in elevation can disturb airflow and influence which waves propagate upward. Researchers can then compare those observations with Mars' general circulation models. Better treatment of gravity wave propagation is likely to be especially important. A model must estimate where waves are generated, how strongly they grow as atmospheric density decreases, and where they are weakened or blocked before reaching the mesosphere. Different explanations make different predictions. A mechanism dominated by local terrain should produce a strong geographic pattern. A mechanism controlled mostly by seasonal atmospheric tides should track particular times of the Martian year across larger areas. A combination of the two should produce clouds only where the seasonal background allows locally generated waves to create enough cooling. New observations can distinguish among those possibilities. A successful explanation has to reproduce several features at once. The atmosphere must become cold enough at roughly 60 to 80 kilometers. The cooling must recur during early southern autumn. Gale has to remain unusually favorable, while Jezero must remain less favorable under comparable seasonal conditions. It should also reproduce the observed cloud altitudes and particle behavior rather than merely generating cold air in roughly the right region. That is what makes the mystery useful. Researchers already have a plausible mechanism and a growing observational record. Continued imaging, better geographic coverage, and more realistic circulation models can progressively narrow the possibilities. Eventually, the same kind of photograph that first looked like a strange rainbow over Mars may become a precise test of how energy and motion move through the Martian atmosphere. And with that framework in place, the original Curiosity image can be read very differently from the way it first appears. On January 17, 2025, during Sol 4426 of Curiosity's mission, the rover was sitting inside Gale Crater beneath the rising slopes of Mount Sharp as evening settled across the landscape. High above it, the atmosphere was doing something scientists are still working to explain. Roughly 60 to 80 kilometers overhead, pockets of Martian air had become cold enough for carbon dioxide to freeze. The process began at a microscopic scale. Carbon dioxide molecules gathered into tiny solid particles. Many of those particles formed under similar conditions and grew at similar rates, leaving parts of the cloud with an unusually narrow range of crystal sizes. Sunlight passing through those particles was diffracted into pale bands of red, green, and blue. What appeared in Curiosity's cameras as a delicate rainbow therefore carried information about the cloud's internal structure. As the particles continued growing, some became large enough to begin settling under Martian gravity. Pale streaks extended downward beneath the main cloud layer. Those falling crystals could descend toward roughly 50 kilometers altitude before entering warmer conditions. There, the dry ice became unstable and sublimated directly back into carbon dioxide gas. The entire event could begin and end high above the ground. Nearby, another part of the atmosphere was behaving differently. Faint water ice clouds around 50 kilometers altitude appeared beneath the higher carbon dioxide layer. In the 2025 sequence, the lower structures moved in a different direction from the clouds above them, showing that separate wind regimes were flowing through vertically stacked layers of the Martian atmosphere. The extreme cooling higher up may be connected to gravity waves. Air displaced upward by terrain or atmospheric disturbances can expand as pressure falls, producing temporary cold regions. Thermal tides, driven by daily solar heating, can modify those waves and alter the temperatures they reach in the mesosphere. That framework explains how carbon dioxide could briefly cross its frost point. It still does not fully explain the geography. Curiosity has seen the iridescent twilight clouds return during corresponding seasons in 2019, 2021, 2023, and 2025. Perseverance, operating more than 3,000 kilometers away in Jezero Crater, has not reported comparable carbon dioxide twilight clouds. Whatever combination of terrain, atmospheric tides, gravity, waves, and seasonal circulation produces the cooling above, Gale appears to favor some regions more than others. That pattern remains one of the most useful parts of the mystery. And Curiosity is observing it from a place that records an even larger change in Martian history. Beneath the rover are hundreds of meters of sediment deposited when Gale Crater contained lakes more than 3 billion years ago. Curiosity has driven across mudstones formed in standing water and examined rocks containing clay minerals, biologically important elements, and chemical conditions that could have supported microbial life. Modern Gale belongs to a much thinner atmosphere. Mars lost atmospheric material over billions of years through processes driven partly by solar radiation and interactions with the solar wind. The lakes disappeared, surface pressure declined, and the environment became the cold desert curiosity explores today. The clouds overhead belong to that surviving atmosphere. They provide no evidence that life exists on Mars. They do not demonstrate that ancient organisms inhabited Gale, and they require no unknown law of physics. Their scientific value comes from something much more measurable. Mars is repeatedly producing a cloud at a location and season where current atmospheric models still struggle to reproduce the required conditions. That gives researchers a specific discrepancy to test. Circulation and waves influence temperature. Temperature determines whether carbon dioxide can condense. Cloud microphysics determines how the crystals grow. Their size controls the iridescent colors, and gravity produces the fall streaks that eventually vanish into warmer air. The recurring geography shows that some part of that chain is still represented imperfectly. So curiosity remains beneath Mount Sharp, watching a sky that spacecraft have studied for decades. For a few minutes after sunset, microscopic crystals made from the Martian atmosphere itself remain illuminated high overhead. They scatter the fading light into color, drift downward through the thin air, and disappear back into gas. And in that quiet cycle, Mars continues to reveal atmospheric behavior that we are still learning how to explain.